Hi everyone, welcome to the next session for design and drawing of reinforced concrete structures. In last class, we have seen about the design procedure of and analysis of doubly reinforced beam section. In today's class, we'll solve some problems based on this design procedure or analysis procedure what you are discussed. First I am reading the problem. After reading of this problem, we'll explain the step by step procedure. We'll calculate the step by step procedure. The problem I am reading here: determine the ultimate moment of resistance of a doubly reinforced beam of rectangular section having a width of 300 mm and reinforced with 5 bars of 25 mm diameter at effective depth of the beam, and the compressive steel is made up of 2 bars of 25 mm diameter at top. An effective cover of 60 mm are provided, and effective cover of 60 mm is provided, and adopt M20 grade concrete and Fe 415 grade steel. This is the problem they are given in the question. If you see here, this is the problem they are explained. They gave the one doubly reinforced beam section. In the doubly reinforced beam section, they are given the width of the beam as 300 mm and effective depth of the beam as 600 mm, and effective cover also they are provided. That effective cover they mentioned in the problem itself as 60 mm, as well as they gave the steel reinforcement in the compression zone as well as steel reinforcement in the tension zone. In compression zone, they are provided the 2 bars of 25 mm diameter bars. 2 number of bars they are provided, and the number of bars having size of the diameter as 25 mm diameter. Again, in bottom zone also they are provided the 5 number of bars with size of the diameter as 25 mm. For this section, they asked to calculate the moment of resistance. They are asked in the problem. That how we have to calculate for such type of problem is, first we have to calculate the limiting depth or maximum depth of the neutral axis. Then you have to calculate the actual depth of the neutral axis. In third step, we have to compare the limiting depth as well as actual depth. In later fourth step, we have to calculate the moment of resistance in compression or in a tension. First I am written here the all the step by step procedure. Step by step I will explain these all parameters. And if you see here in this given condition, they are given the width of the beam section as 300 mm and the depth of the effective depth of the beam as 600 mm. If you see here, they provide also the effective cover. That means if you want to calculate the total depth of the beam, effective depth plus central distance of the bar plus how much amount of clear cover or what is the stirrups you are providing, if you substitute all these parameters, you can calculate the total depth of the beam. As well as they are given the grade of concrete as FCK. That FCK they are given as M20 grade of the concrete. M20 grade for FCK, characteristic strength of the concrete equal to 20 Newton per mm square. As well as they are given the yield strength of the steel. That yield strength of the steel Fy equal to 415 Newton per mm square. Where the area of the steel they are given in the bottom zone as 5 number of bars of 25 mm diameter. In top zone they are given the nothing but in compression zone they are given the 2 bars of 25 mm diameter. This is the formula for calculation of the area of the steel. The calculation of area of the steel, AST equal to N into pi by 4 into D square, where N is the number of bars given in the problem. Pi by 4 D square is the cross sectional area of the diameter of the steel rod. Here in tension zone they are provided 5 number of bars, hence 5 by 4 is the value of 0.785 and the diameter of the bar as 25 mm. If you calculate all these parameters, we will get the area of the steel in tension reinforcement as 2454.36. In some situations, without giving this number of bars and the size of the diameter of the bar, directly they will give the area of the steel reinforcement in the tension zone or area of the steel reinforcement in the bottom zone, as directly they will give this problem. In those condition also you can take that area of steel value. Again, if you see here, area of the steel reinforcement in the compression zone. In area of the steel reinforcement in compression zone, they are given as 2 bars of 25 mm diameter rods. Two number of bars with 25 mm diameter. And again, if you substitute n into pi by 4 d square, where n is the number of bars, pi by 4 d square is the cross section area for the steel bar. 2 into pi by 4 into where diameter of the bar is 25 mm. If you substitute these parameters, we are getting the area of the steel reinforcement in compression zone as ASC equal to 981.73 mm square. This is the area of the steel occupying in the compression zone, and this is the area of the steel occupying in the bottom zone. Up to now, this is the given parameters. Next, we will see the step by step procedure. The first step is limiting depth of the neutral axis or maximum depth of the neutral axis. Step 1, we are having the limiting depth of the neutral axis or actual depth of the neutral axis. If you see here, this limiting depth of the neutral axis also, they are given in the code book IS 456. That XU limit equal to limiting depth of the neutral axis, XU limit equal to K into D, where K is the neutral axis constant and D is the effective depth of the beam. If you consider here for our grade, they are given in the problem it as FE 415 grade, hence why we are taking this value as 0.48. Suppose if they are given this grade of steel as 250 grade, in those conditions we have to take instead of 0.48 we have to take the 0.53. And limiting depth of the neutral XU limit equal to K into D, 0.48 into where D is the effective depth of the beam. And if you substitute these parameters, you are getting this limiting depth as 288 mm square. This is the step 1. And while calculating the actual depth of the beam for doubly reinforced beam section, we have to calculate the stress compression of steel. The steel bars we are providing in the compression direction, in compression phase. For this steel bars, how much amount of stress is acting, that also we have to calculate. It will be useful for calculation of actual depth of the neutral axis. That is nothing but stress in compression reinforcement, FSC equal to, we are having the formula already while deriving the analysis of doubly reinforced beam, we have analyzed where FSC equal to 0.0035 into 1 minus D dash divided by XU max. This is the formula for FSC. FSC equal to 0.0035 into 1 minus D dash divided by XU max and into ES, where E is the modulus of elasticity of the steel. If you having the code book of IS 456 2000, in code book of IS 456, based on this FSC value, by seeing the table value, we can get the FS value directly. If you substitute this 2 into 10 power 5, directly we can calculate without code book, we can calculate the FSC value. Again, if you ensure that the stress in steel in compression, it should always not should be greater than 0.87 into Fy. The compression in steel what you are getting, it should not exceed this 0.87 into Fy, where 0.87 is the numerical value, Fy is the yield strength of the steel. That is nothing but FSC equal to 0.87 into Fy. 0.87 into Fy is the yield strength of the steel 415 grade, and if you substitute, you will get the stress in steel in compression zone. In this compression zone, the stress of in steel is getting as 361 Newton per mm square. Next, we are having the formula for total compression force equal to total tangential force for a doubly reinforced beam section. For this doubly reinforced beam section, we are having total compressive force C equal to 0.36 into FCK into BXU plus ASC into FSC minus 0.446 into FCK. This is the total compressive force acting on the doubly reinforced beam section. Already we have discussed in our previous lectures. And again, if you see the total tangential force acting on the doubly reinforced beam, that T equal to 0.87 into Fy into AST1. This is for limiting moment or limiting moment for the area of the steel for the limiting moment resistance, and 0.87 Fy AST2. This is the one more area of the steel requirement for the additional load. For calculation of this AST2, based on ASC value, for calculating the actual depth of the values, we are calculating the area of the steel. That AST2 equal to, this AST2 equal to nothing but ASC into total compressive force equal to total tangential force. AST2 equal to ASC into FSC minus 0.446 into FCK. By using this, we can calculate the area of the steel AST2. AST2 equal to ASC into FSC minus 0.446 into FCK divided by 0.87 into FSC. Where this ASC is the area of the steel reinforcement, already we are calculated. This ASC is the area of the steel reinforcement. FSC value already we have calculated by using the formula 0.87 into Fy, that 0.87 into Fy as 415 Newton per mm square. If you observe in our code book, they are not considering this 0.446 FCK value. If you provide this limiting value, that characteristic strength also, it is giving very less value. If you are deducting this value also, if you are keeping this value also, it does not give that much difference. And if you calculate the area of the steel, that area of the steel in second phase additional moment, I am getting it as 957.4 mm square. This is the area of the steel for the additional moment. We know the total area of the steel, we know the second area of the steel for the limiting moment, for maximum moment. If you deduct the total area of the steel with the area of the steel in second zone, you will get the area of the steel for the second steel reinforcement. This is the how we are calculating the area of the steel in first phase for limiting moment, as well as area of the steel for the second phase. Next we are having the one more formula, actual depth of the neutral axis. This actual depth of the neutral axis, we are having the formula total compressive force equal to total tangential force. The total compressive force nothing but 0.36 into FCK into BXU. Total tangential force equal to 0.87 into Fy into AST1. For calculating this AST1, we have solved this much procedure. In suppose in some situation, they will directly give this area of the steel AST1 value. In those conditions, you need not to do all these procedure. Directly you can substitute the area of the steel 1, you can calculate the actual depth of the neutral axis. That 0.36 into FCK into BXU equal to 0.87 into Fy into AST1. That XU equal to 0.87 into Fy into AST1 divided by 0.36 into FCK into B, where 0.87 is the numerical value, Fy is the grade of the steel they are given in the problem as 415 Newton per mm square, and AST1 is the area of the steel reinforcement for the limiting moment, that is nothing but 1496.8 mm square, and 0.36 into FCK into B, where FCK is the characteristic strength of the concrete, and if you substitute the width of the section as B 300 mm, we will get the actual depth of the neutral axis as XU equal to 250.19 mm. This is the actual depth of the neutral axis. Now what we have to do means we have to compare the both XU limit value as well as XU value. If you see here, XU limit value we are having 280, sorry, XU limit we are having 280 mm. This XU limit we are having 280 mm. This XU value we are having 250.19. When XU is less than XU max or XU limit, this condition we are taking it as a under reinforced beam section. This condition we are taking as a under reinforced beam section. For this under reinforced beam section, we have to calculate the moment of resistance in compression or moment of resistance in a tension. You can either use area of the moment of resistance for tension as well as moment of resistance for compression. For moment of resistance, if you are considering as a compression zone, then you have to use this formula 0.36 into FCK into BXU D minus 0.42 into XU plus ASC into FSC minus 0.446 FCK into D minus D dash. If you substitute all these parameters in the above problem, in the above equation, you will get the movement acting on the beam as 454.13 kilonewton meter. This same formula, instead of this compression direction, if you substitute in tangent direction also, you'll get the same value. That movement is nothing but mu equal to 0.87 into Fy into AST1 plus 0.87 into Fy into AST2. If you substitute the AST1 as well as AST2, you will get the same moment acting on the beam section. This is the complete analysis of design of doubly reinforced beam section. In later class we will solve some more problems based on this same concept. Again, you have to remember step 1, limiting depth of the neutral axis, step 2, actual depth of the neutral axis, step 3, comparison of the section, step 4, moment of the resistance. Whereas for doubly reinforced section, for calculating the actual depth of the neutral axis, always remember that stress in compression reinforcement is required. Why? Because to classify the area of the steel reinforcement in additional section as well as for the limiting section. Thank you.